Hi, everyone. Welcome to Foresight's Biotech and Health Extension Group, sponsored by 100 Plus Capital. I am very thrilled to welcome all of you for, I think, what will be quite a special meeting today. It has taken me almost a year to set this up. And so I'm really, really happy to have Alexander join today. Basically, around Irina's conference, previous presentation on plasma dilution, there was lots of interest in the group to explore this further. I then did some digging and then over through a few recommendations, found a Russian biohacker group who has been doing self-experimentation on plasma dilution. But most of their stuff was in Russian. It was very hard for me to read. And I tried to contact them. It was very difficult. But then finally, someone here else in the group helped me reach out. And that was half a year later. So it literally took me half a year to finally got that connection. But now finally we have Alexander here. And little did we know, he also proposed a 10th hallmark of aging. So I'm going to share much more info on Alexander in the chat, but today he'll be talking about biohacking as a necessary component of health extension. And really, really happy to have him here. I should also say he has been pre-admitted to be a 2022 Foresight Fellow. So you will be seeing much, much more of him over the next year. With that, without further ado, Alexander will talk for a little while. Then we may have some discussion that will be on the record. Some will be off the record. I will share more info on Alexander's work here. I'm super happy to have you here. Thank you so much for joining. You can't, it's hard for you to know how many people here in this group have been looking forward to this. So thanks a lot for joining and welcome to the group.
Thank you, Alison, for a warm welcome. I'm happy to be here and I'm excited to talk about our work. I'm here on behalf of our group of enthusiasts. Our group is called RLE Group, which is not surprisingly stands for Radical Life Extension Group. Very simple, but true. And we basically try to research and try out different longevity like interventions on ourselves and do many more things. And I will tell about some of the projects today. Let me share my screen. All right. Can you see the slides? Awesome. All right, let's go forward. I would like to start my presentation with the words of brilliant scientist, Nobel Prize winner Richard Feynman, who pointed out there is no physical law that could limit our life longevity. And this is basically what motivates us, what drives us to reach the radical life extension. And how do we in RLE group define radical life extension? Because of course this is ambiguous term. Some people could define it as 10% increase. Some could define it as 10,000-fold increase in life expectancy. But we define it as at least twofold increase in life expectancy. But the ultimate goal for us is, of course, achieving longevity escape velocity. I hope that you are familiar with this term, longevity escape velocity. And I'm actually proud that here, we have here in the call person who advocated for this term. And basically, longevity escape velocity means that every year the progress in science and technology adds additional year for the life expectancy. So eventually, this should be our goal. But let's see how far are we currently from reaching this goal, this ambitious goal. In my presentation, I would like to answer 3 questions. Why biohacking is basically the necessary component of a strategy for radical life extension. How and how we do biohacking in our group, and what we have already achieved. So why we do biohacking? First, let's try to analyze how far are we from achieving the longevity escape velocity, right? And to do that, I have um, I have gathered the data from European public data banks and plotted the increase in life expectancy on the graph. Here we have years on the x-axis. Here on the y-axis we have life expectancy in different countries. I did regression. I um, like made a regression lines here, and the slopes of this regression lines tell us how many years we gain on average, like in particular country, how many years of additional life expectancy we gain every year. And we see that in some countries we gain, like in Belgium, 0.27 years every year, and so on, and like very similar numbers in other countries. But on average, we gain 0.25 years every year. This is life expectancy at birth, and it looks pretty okay. So, like a linear trend, constant linear trend on increasing life expectancy. But in fact, this this increase in life expectancy is not that big, because, for instance, if the trend will continue, 30-year-old can uh, can like have 50 additional 15 years or 16 years to the current life expectancy. So it's not a dramatic increase, even with this kind of progress, like linear progress. But this is a life expectancy at birth. And if we look at life expectancy at 65 years, we see that slope here uh, became gentler. So the life extension is not uniform across age groups. And if we look at life expectancy at 85 plus years, it flattens out almost completely. So it means that the current progress in healthcare, it doesn't account for deaths at advanced ages, right? At 85 plus years. So basically, we can say that the current progress doesn't involve aging. So we do not have interventions against aging itself per se. And this infographics tells us that, okay, life expectancy at birth increases by every 4 years by 1 year. Life expectancy at 65 years increases every 6 years. And life expectancy at 85 plus years old increases every 15 years. This means that many of the people, if not all, aged 80, 85 years or older, they are virtually doomed with the current progress of medicine, and maybe even like younger people as well. So we can clearly see this from this graph from this scientific paper, which shows us clearly what's the reason of that. Here we see two graphs. These graphs are mortality rates on a logarithmic scale. So, in fact, these are exponential functions. And the blue curve corresponds to the mortality rates of so-called poor people, and like red curve is mortality rates of quite rich people. And we see that the difference in mortality at 40 years is huge, but then it shrinks towards zero at advanced ages. It means that the current healthcare cannot actually prolong significantly life of old elder people. Like, and this is when like the new medicine, the new healthcare, like new advances in science and technology should come into the arena. But what is the current state of affair in in the longevity field, in the research field? So it's also quite the study. It's probably not the most optimistic because the study by Pedro de Magalhães, I don't know how to pronounce his surname correctly, so I'm sorry if I'm mispronouncing his surname, showed that actually the out of almost 30 uh, like life extending genetic manipulation in mice, only two of them showed signs of demographic aging rate retardation. So what does it mean in practice? What does it mean, like demographic aging rate retardation? So let's take a look at these graphs. These graphs are called survivorship curves. And let's say that a yellow curve represents the control population, control cohort. It may be like people, for instance. So, and the green curve represents the aging rate retardation. So the intervention that actually decreases demographic rate of aging. And we can see how dramatic is maximum lifespan improvement. So all other cohorts have already died out, while like almost half of the green cohort are still alive. So this is what happens when we influence the aging per se. So the blue curve here represents what represents the intervention types that we have already discussed previously. So the current health care. So it extends life in the beginning, so like virtually no mortality here. But then two curves like converge because the like the mortality rate decrease here is pretty negligible. And this is not what we want because we want to increase like the maximum lifespan as well. Luckily, we don't necessarily need right now to retard aging rates to achieve like maximum life extension, maximum lifespan extension. We have so current genetic interventions in mice also extend maximum lifespan, but they do it via so-called like parallel transfer of the survivorship curve. So they do not retard aging rate, but still they they demonstrate quite decent improvement in both median lifespan and maximum lifespan. And this is what we wanted to develop. And this is what we wanted to see from our big pharma. But what happens with big pharma? We see that this process of adoption is pretty slow. On average, it takes like 12 years uh, to like adopt a drug or intervention from preclinical trials to market. And there, the failure rate is tremendous. Only 1 in 1,000 of new drugs uh, end up end up like end up in like market. So the and currently there are not much anti-aging drugs that are in development. And this is a like sad story. And this is why we need biohacking, because biohacking can can speed up the process of an adoption of different already known interventions like dramatically, but only if biohacking is done right. And I will tell how we do biohacking. Uh, like yes, so biohacking done right. So we identify three main pillars of like so-called we call it like correct biohacking or like intelligent biohacking. So first, usage of mathematical framework for evaluation of potential interventions. So we need to understand how promising is the interventions, how many years on average it can add to the lifespan. Is it worth it to even like to be even tested, right? The second main pillar is to avoid typical experimentation mistakes, because experimentation, and especially self experimentation, is not an easy thing. It You can fool yourself easily if you do not do everything correct from statistical point of view and like yeah. And the third main pillar is to if you want to defeat aging in the end, you must understand what is the underlying cause of aging. And we are also developing, doing theoretical progress in that direction. I will expand on this uh, in the next slides. So first of all, we developed a mathematical model that is able to convert risks of all-cause mortality to additional years of life. Because many studies that you can find on PubMed or like other databases, they report, relative risks of all-cause mortality and something like that, or odds ratios or whatever. But these quantities are not intuitive. You can like basically it's hard to tell whether risk reduction of 10% worth it. So worth to test a drug or something like that. Or like any other interventions, for instance, dietary interventions. Okay, so some studies showed that it like consuming I don't know, like vegetables reduces risk of all-cause mortality by 5%. Is it big increase in life expectancy? Is it small? Uh, People usually don't understand. And we have developed a model that converts these risk reductions into the pretty intuitive and easy quantity, additional years of life expectancy. And we have you can play with our demo of our framework, which is very simplified but reflects the concept. All right, so this is enough about it. Let's talk about the experimentation mistakes. The first experimentation mistake, so the first trap of self-experimentation, is that many biohackers do not account for the statistical phenomenon called regression to the mean. The regression to the mean, uh, I can explain with a simple words what does it mean. So every like most of the biomarkers, especially blood biomarkers, they have uh, natural variability. So they vary over the time, and some of markers, or many of markers actually, they vary pretty with high amplitude, and the variance is pretty huge. And accidentally, if you take one measurement before the experiment and after the experiment, before the experiment, you might actually accidentally measure your biomarker at the peak, and after the experiment, you can measure your biomarker at the trough of the natural variance. And then you can erroneously conclude that the intervention led to the decrease in this biomarker of interest. But in fact, it is a mistake. So it was just to natural variance of the variance of this marker. To avoid that, we first of all try to pick markers that have quite small variance, right? So they are pretty robust, stable, and ideally monotonically increasing with age, or nearly monotonical increasing with age. Uh, but for highly variable markers, we do the following procedure. We have a history of measurements per person, so we can uh, plot a distribution. We can create a distribution of values, and we can say, okay, this value seems to be an outlier. It is unlikely that it came from the distribution of previous values for that for that person. So we can say that it is unlikely that this value was due to natural variance of this marker. All right. The next experimentation is taking how we tackle it. P-hacking. Typically, biohackers, they do they measure plenty of markers at once. So they measure like panels of biomarkers where uh, some biohackers have like hundreds of biomarkers in their panels. And by pure probability theory, you can have like due to random fluctuations, you can have several biomarkers. You can have like statistically significant difference in at least several biomarkers, just due to lots of comparisons. Mm, And to avoid that, we apply sophisticated statistical methods in our experiments, like Benjamin-Hochberg procedure for multiple comparison correction, and so on. So this also helps. This is of course not the silver bullet. It doesn't say automatically that our experiments are free of false discoveries, but at least it improves the chance that we will discover something meaningful, not just random noise. And the third pillar, the deep understanding of the biology of the agent. So we believe in the group that current current uh, view of the aging process in the academia is cell-centricity, right? So many of the laboratories, like scientists, they focus on cells. They do epigenetic reprogramming. They manipulate NAD plus levels, kill senescent cells, whatever. But they completely overlook the changes that are happening to the environment of these cells, namely extracellular matrix, which is comprised of long-living proteins like collagen, elastin, and or like all of you probably know that these proteins undergo chemical modifications like glycation. And glycation leads to cross-link formation, to adducts formation, and so on and so forth. And these actually, we have shown in the paper that these changes to long-living molecules can lead to, uh, via various mechanisms, can lead to virtually all hallmarks of aging. So they can cause these hallmarks of aging. And the true underlying cause of aging might be just this damage to the extracellular matrix where our cells reside. And to give a bit more context, I want I won't go here too deeply into details, but I would like to present some facts and hypotheses. So, for instance, we can see here that that old stem cells, mesenchymal stem cells, planted like placed on a ECM extracellular matrix from younger mice, they expand like young cells. So they preserve the traits of young cells on the younger matrix, while the uh, younger cells, like 3 months old cells, while being placed on ECM from old mice, they display traits of old stem cells. So they divide less, they have like specific biomarkers of old cells, and so on and so forth. And this is my hypothesis that I'm advocating for is what causes the cellular senescence phenomenon? Well, basically, it is not a surprise. It's not something new that senescent cells are actually playing a role in wound healing, even in younger people. So these senescent cells mainly counteract fibrosis. And my hypothesis, hypothesis, like explains the accumulation of senescent cell the following, in the following way. Um, since senescent cells counteract fibrosis, then changes to extracellular matrix during the aging, like stiffening, matrix becomes resistant to collagenases and so on and so forth. It mimics the fibrosis, and cells erroneously think that there is a fibrosis and can turn into senescent cell and start doing their job to counteract the fibrosis. So in a way, you can call as like aging pseudofibrosis. Yeah. So this is my hypothesis. We are also working on experiments that will either confirm or deny this hypothesis. But yeah, I would like to share this. And we believe that the eventually what can lead us to radical life extension to like the longevity escape velocity is exactly the therapies that can rejuvenate this extracellular matrix, make it young again, like break down the crosslinks due to glycation. Currently, it is problematic. So we don't have any glucose pain breakers, but we still can do something to matrix. And I will tell about it a bit later. So what we can do already now. All right. So now let's discuss what we have already achieved and what we plan to do in the future. So these are main areas of research and development that our team is focusing on. So first main thing that this is the first thing that we have tried in the beginning when the group was formed is drug repositioning. So we look for papers where different drugs are researched, and where people like describe some anti-aging properties of different drugs. We collect information. We identify underlying pathways that these drugs target, and so on and so forth. We have also computational models, and we try these drugs on ourselves. And I will later tell a bit about our first experiment, successful experiment with drug repositioning. To test these drugs, we need something that we can measure, and we identify suitable biomarkers. We develop new biomarkers like composite biomarkers, panels of biomarkers, and so on and so forth. Mathematical modeling, I've already mentioned that, and gene therapies. So we started developing our own gene delivery system uh, like recently in 2021. So I will also cover this topic a bit later. And briefly, what are our main focuses? But we are not limited by that. This is just what we are targeting right now. So musculoskeletal system to counteract sarcopenia, circulatory system. We are trying to remove atherosclerotic plaques and increase elasticity of our blood vessels, and cognitive function, of course. So this is a timeline with our progress. So we have started as a group in 2015, and then in 2016 we conducted our first experiment, and in 2020 the our probably most famous experiment happened, like therapeutic plasma exchange research. And in 2021, we continue with gene therapy development and more other smaller trials. Let's talk about our history. So in 2016, I worked on the data set analysis. I had huge table with uh, lots of biomarkers from one gerontological center in Russia. And I was analyzing the data and found out that uh, several markers of arterial health were were strongly correlated with uh, like actual age of people, and that I decided to like build a regression model uh, to predict the basically age. And I was surprised that the model that I built eventually uh, it it likely was not only the model for predicting chronological age, but it was also uh, a pretty good predictor of overall health. And for instance, people with diabetes and hypertension, they have significantly higher biological age. And this biological age was mainly driven by four factors: carotid intima media thickness, pulse wave velocity, degree of stenosis, and augmentation index. So only four biomarkers give the error of 6 years and likely represent biological age estimation. And remarkably, the most significant biomarker in this index, carotid intima media thickness, it happened to be a very, very robust biomarker. It was very stable, almost monotonically increasing with age. So it was very hard to reverse. And there are very, very few drugs that could do this, could like reduce the carotid intima media thickness. And but we have managed to find a drug combination that exceeded our expectations. So we have found that drug combination valsartan plus fluvastatin reduces the carotid intima media thickness almost twofold in both of our volunteers, and these are our co-founders, Stanislav and Yuri. And this reduction was pretty stable. It persisted for about a year, which is remarkable, I think, because I have seen lots of records about the progression of carotid intima media thickness, and it's very stable biomarker. So another biomarker, very important biomarker in this model, is pulse wave velocity, which reflects the arterial stiffness. It is um, it is pretty variable biomarker, or like opposite to carotid intermediate thickness, and hence we needed a device that could allow us to measure it like multiple times before the experiment, after the experiment, to like average our measurements and do more um, like statistically robust conclusions. But there are few devices that can accurately measure this biomarker on the market, available on the market, and that's why we developed it ourselves. So we are biohackers in the end. So yeah, the first prototype, we like used it already for our trials. We took our learnings from that, and we are working on a next version, which will hopefully uh, be out next year. So yeah, looking forward for that. So another our achievement is basically the plasmapheresis, which is pretty famous in certain like yeah, and like pretty famous. I don't know, because other our interventions are not that experiments are not that famous. Um, so we conducted this. We didn't ex- we didn't expect to observe like dramatic improvements in biomarkers that we can like treat as super promising and so on and so forth. We just wanted to basically understand how we can do that, like the logistics of the whole process, because it was so you need to replace half of your plasma with the selling and like plus albumin, and this is not a simple procedure, this is not a standard procedure, but we've managed to calculate how many plasma you need to donate at each like visit to the doctor, and then how many albumin you need to replace. And we did this. And surprisingly, we have found like pretty interesting changes in our biomarkers of this gentleman. We have found that, for instance, contrary to our expectations, for instance, cholesterol, it goes both directions. So the bad LDL, bad considered as bad, it goes down, and the HDL goes up, which is pretty interesting. But of course, we have like only two data points, now more, of course. So we cannot draw conclusions out of that, and that's why our friends and colleagues, members of RLE group, um, we have started a clinical trial, and you have this identifier here. This clinical trial aims to compare plasmapheresis with albumin and without albumin, because it's interesting which role albumin replenishment plays in the whole procedure. So you can use the QR code to access the article about the our experiment. Yes, and next thing. Yeah, so here are smaller things that we have achieved. We have tried various senolytics, uh, FOXO4-DRI peptide, physitin, other drugs, our human volunteer took. And but the thing is that even though the volunteer was like 57 years old, we haven't found that much senescent cell in his body, and so we cannot say whether they work or not. So probably we need someone older. Then we also created a lentiviral vector for ApoA1 Milano gene delivery. We also tried microbial replacement experiment. We can expand on that later. It's pretty interesting stuff because we have a collection of microbiota from Soviet cosmonauts. They are considered to be like super healthy men, and we have a hypothesis that this microbiome, like being transferred correctly, can basically yield some very, very nice health improvements. Yeah. So what's next? Here are several things that we are planning to deliver in the upcoming years. First of all, we are very intrigued by the article which showed that targeting the enzyme 15 PGDH, which uh, basically reverted muscular aging. So, and we are very intrigued by that study and want to reproduce on ourselves. We also aiming for epigenetic rejuvenation of hematopoietic stem cells via targeting CDC42. It's pretty also well-known target. Why? So this is probably one example of cells that cannot be rejuvenated by placing them in younger environment. So the hematopoietic cells are pretty reluctant to the changes. It's like to reverse in aging uh, using this like methodology, but we can reduce their like reduce their epigenetic age by targeting this enzyme, this protein. And but then if they are in the old environment, they age again. They become senescent again. And so we plan also to investigate how we can maintain the useful environment for these rejuvenated cells. So this will be a very, very interesting long journey. And the third point is actually very, very important. I've mentioned that there's something that we can do with HECM already now. And this is targeting elastogenesis. So elastin is now considered to be one of the longest living protein in our body. It basically, it is, there is a consensus in scientific community that elastogenesis is limited to like early infancy, and then they like all synthesized elastin like basically remains in our body, and then it accumulates calcium, also is degraded by enzymes and so on and so forth. We lose this elastin, and this leads to progressive deterioration of different tissues, not only blood vessels, though it is very, very important, but also skin, lungs, and other like our ligaments, muscles, and all tissues lose their elasticity. And this is like crucial for not only for our appearance, but also for our functional health. Because, for instance, rigid blood vessels, they lead to damage of organs because they do not dampen the blood flow, and that's why the fast moving blood flow, they damages sensitive capillaries in brain, in kidneys, and other organs. Also, the this fast blood flow, which is not dampened by the elastic aorta, it creates turbulence, and this turbulence puts enormous load on left ventricle of our heart, and this causes hypertrophy, cardiac hypertrophy. Then hypertension is also um, can be caused by this aortic stiffening and so on and so forth. And we can try, and we already have some drugs and other methods to increase um, production of elastin, like in vivo. We will try it. And the fourth main thing is development of anti-aging gene delivery system. So, and this is actually what we have tested already. So we have already experimented on these animals. I don't know how to. Sorry, I forgot how to call these animals in English. This is my bad. Sorry, but yeah, we have got our first promising results that it might work actually, and we are developing this uh, simple and uh, simple and um, safe gene delivery system that we aim to use for delivering some anti-aging genes and achieving like pretty pretty I don't know, but I at least hope that we will achieve with this gene therapy pretty impressive increase in life expectancy in the future. So our team, we are currently five of us. Yeah, but we're expanding and yeah, developing our efforts in like achieving radical life extension. Yeah. Thank you for your attention. It was a pleasure to present our stuff here and ready for questions.
Thank you so much. Wow, you have lots of questions here. I will stop sharing your screen for just a second.
Sure.
This was a lot of information. I will download the chat and send it to you because there's lots of discussion on your work in it. And people have actually been going through the motion and posting most of the articles that you mentioned in the chat already. So that's great. Um, okay, let's see. So, oh my God, we have lots of different questions. Um, I guess let me know in case I'm missing on someone because usually I ask that you start them with a Q, but not everyone did this. I have one that is from Dima, one from Alex Chen, and then I'll get back with a few others. So Dima, you're first.
Yeah, so my question was regarding the progress you experienced so far and when whether it convinced you that biohacking can be impactful. I don't know, you can sort of claim as well if you think it was already impactful and why and at what point that you decided that it's kind of a worthy investment of time and money.
Yeah. Well, basically, my interest to the life extension topic began in 2012, and at that time, I strongly believed that we will defeat aging with short within 5 years. But then, uh, then radical life extension was still very very far away, and I started digging the material, started analyzing literature, analyzing, trying to dig into these signaling pathways of aging, trying to understand why the progress is still there. Why don't we have this rejuvenation therapists? And then the critical mass of information accumulated, and the strategy of radical life extension emerged out of that. So we understood that actually the cause of aging might be and likely to be in the ECM, in the cross-links glycation, and it will take pretty a long time to find ways of how to rejuvenate this vast majority of long-living molecules, because it's not an easy task, and therefore we need some ways to win some time before that, because it easily can take 2 or 3 decades until we get to the point when we will have these age breakers or other techniques that can basically rejuvenate our matrix, extracellular matrix. So I hope I at least partially answered the question, but it's really hard because I can speak about it like hours, and we probably don't have so much time.
Well, I hope we can stay on for a little longer because we have lots more questions. Next one up, we have Alex Chen. Okay, then we have Mika.
I got a few questions. I'll start with one and then let someone else go after me. Then I'll ask my other ones after.
Sure.
Yeah. Do you have any ideas on how we can do better at educating potential biohackers about the common pitfalls you mentioned at the start of this talk? Like, how can we avoid other people who want to get into biohacking kind of not making the same mistakes?
Well, that's a very good question. Basically, probably we might start some initiative where we will accumulate best practices, create some like like create some hub where we will accumulate best practices, which will which will tell people how to avoid different mistakes, right, and how to be safe during this self experimentation, and probably maybe even because it's actually a very risky thing, and the biohackers are really brave men who try out new things, and many so-called biohackers, they just wanted to be like I don't know, like they probably do not realize what is biohacking. Maybe it's like something fancy they want to try, but in fact, it's very risky thing, and it's probably a good thing to accumulate some knowledge somewhere and like advertise this place where all the materials will be, which will basically say how cool is that, and on the other hand, how dangerous is biohacking, and how to do it properly, like avoiding some statistical mistakes and so on and so forth. So yeah, so we need probably a centralized place where we can accumulate all this information and then spread it over the internet, spread the knowledge about this website or something like that.
Great. Next one, we have Josh.
Hey, Alexander. My question was on how
Hello.
often do you guys control for like co-founding variables just in like lifestyle? Like, do you track your like sleep, exercise, and diet daily to make
Yeah,
sure?
sure. Of course, we do. We have like uh, variables, wearables,
Yeah.
like uh, like um, like Fitbit device, right? So where we can see what was the distribution of activity back then, back before the experiment, during the experiment, and so on. But for instance, so what we think is that the control for confounders is especially important when the effect size is very small. So then different confounding variables play a huge role. But for instance, if you have like Alzheimer disease, right, and then you suddenly after intervention got like dramatic improvement in cognition, so it doesn't really mean what the lifestyle was, because it has pretty limited influence on the cognition during this condition, right? So we are trying to pick up markers that are very, very stable and aren't easily influenced by changes in lifestyle. So to increase robustness of our findings. So this is the main idea, to pick up like very, very stable markers, like I've mentioned, carotid intima media thickness, and so on and so forth. And of course, try to keep the same lifestyle as before. And we can, of course, track this by analyzing our activity data from variables. Yeah, this is it. Thanks.
Aaron with a short question.
Yeah. Alex, how old are you?
34 this year. I'm turning in December.
Okay, next one up, we have John.
And sorry, I will add a couple of words to the previous question. Unfortunately, I'm too young to like do interventions myself and see the results. But still, I also try to take all the pills, all the drugs, like others do, because I would like to test like safety of interventions. But I cannot see the effect on me because apparently I'm too young and have pretty good biomarkers.
Hi, Alexander.
Hello.
Sorry.
Hi, Alexander. I hope you can hear me okay. My internet connection's a little bit unstable. You showed a nice chart of all-cause mortality, and I wondered if you have access to some data that excludes things like accidents and injuries and war, so that we can look
Yeah.
more focusedly on age-related diseases.
Yeah, I think it's already, this data is filtered, so it's like deaths from natural causes. By the way, are you that John Ferber who wrote a paper on like glucosapine breakers, like as a future therapeutic for like aging?
I am. I presented at a SENS conference.
And I was also inspired by your work, and I cite your paper, and I found it like brilliant. Yeah, and that's arguments that enzymes probably cannot do too much to crosslinks because they are too large and cannot fit between the collagen collagen strands. This is like very smart, and I also share your concerns about that.
Oh, I'm so glad that you got to see that. I chapter 19 of the Future Aging, which is a book that Greg Fay edited in 2010. So my thought was, maybe what we need to do is genetically engineer fibroblasts to do a better job of turning over the extracellular matrix.
Yep, I totally agree with you, but I think it will take a lot of time until we get to the working therapy on like like speeding up the turnover of the extracellular matrix, and we definitely need to win some time to be able to reach this.
Meanwhile, we do have a small molecule that is able to take care of some of the cross-links in glycation called allegibrium.
Yeah, ALT711. Yeah.
Yes, I've been making that in my laboratory. So if people want to experiment with it, they can contact me.
The decarbonyl crosslinks.
That's correct. Yes.
Okay.
I thought it mostly didn't work except in dogs. There was already a clinical program in a company
that's not true, but we can discuss this in another discussion.
Yeah, I would be happy like to discuss that. Really.
This is the content of one of Aubrey's ending aging chapters, is the story of allegibrium.
I know. I think there's some in Michael Ray's chapter.
Well, we are going to do a follow-up on this. So maybe that's a really good one to tie into that one as well. Someone wanted to ask me, what are you doing personally, Alexander, in terms of health extension? And then also, how do you avoid microplastics when doing plasma dilution?
Since I'm relatively young, I'm not doing anything special. Just physical exercises, trying to keep my diet more or less healthy. And try to avoid like accidents. But other than that, I'm not taking like supplements on a regular basis. Maybe maybe. Yeah, I'm actually, I would like to point out, for instance, I'm actually advocating for actually insulation. So like people avoid sun, but I think that it is incorrect. I will not like discuss this too deeply in this meeting, but I would like to maybe talk a bit about it later. Yeah. So regarding the second question, what was it? Microplastic during the plasma dilution. We don't do anything about that yet. We will evaluate the importance of this factor in future. So we just tried this like as a pilot study, and we haven't really came up with the best way of doing plasma dilution yet. So we are still on the way of researching this. Thank you for the idea, by the way.
Thanks. It was not for me. I'm just
Yeah, I'm
the
answering.
microphone. Yeah.
Yes.
Next one up, we have Jean.
Hi, Alexander. It's very nice
Hello.
this opportunity to hear about your more recent work.
Likewise. Thank you for your email.
Yeah,
And it
I've been
very
on
warm rewards.
your 2020 review. Anybody who listened, I think it's very important in the context
Thank you.
of understanding aging. So with that in mind, I was very interested to see your third point on what's next regarding elasticity.
Hmm.
I think is very important, of course. Um, and you mentioned, re-expressing elastin, but I'm wondering what the limitations of that are if you're not removing the old damaged elastin, right? So you could even make things worse potentially if you don't remove the old elastin,
That's correct.
accumulated damage, right? So yeah, what are your thoughts on that, and more broadly about this type of approach for other, um, molecules, macromolecules that accumulate stochastic covalent damage over time?
That's correct. But there are studies that um, are promising so there are some types of drugs that increase the expression of tropoelastin gene and actually say mice or rats that took these drugs, they have more elastic over throughout the time, and the elastin was properly organized. So this gives us hope that simply stimulating the expression might work, but of course we won't take it first on ourselves. We probably try it on some animals. Yeah, and of course, tropoelastin expression is not the only thing that might be needed to restore the elastin network, because elastin is a complex protein comprised of several like monomers. And the main structure, the main framework of the elastin is made of fibrillin. So we might also need to overexpress this protein. Yeah, it's a very, very difficult to say in advance how it will turn out, but we will see. This is the only thing that I can tell right now. And for that, of course, we need like lots of experiments, support, and other stuff. But if we won't do it, nobody will.
No,
Because
I'm glad you're going to try it. And there's also the collagens that accumulate damage over time that
exactly,
get turned over because of that damage.
yes, exactly. So
The big
they become less uh, like less susceptible to collagenases, as I'm pointing out. But at least at least on the skin, in the skin, we can try to apply some interesting method. So, but I will keep it silent for a while. Maybe if we will succeed, I will tell a bit
Well,
more about that.
We will have
Right.
to have it back for several occasions. Next one up, we have David Gowell.
Thank you, Alexander, for your fine presentation. I appreciate it. Um, so we have many individuals who tend to come from an engineering or biological engineering background who are 35 or younger, such as yourself, who are working on biohacking. But it seems to me that the correct population to do this would be those where it would be clear whether a thing is actually having an impact or not, whatever the thing is. And so that the focus of uh, biohacking would be better focused in the 65 to 70 year age, where it seems to me, and I can't prove this, that you have remaining normal functionality, whereas, no offense to anyone on this call, 80 to 90 might be a little bit too late for some elements of our complement of humanity, our bodies. Um, and so I don't know, in your research, I'm interested, how many of the folks doing biohacking using your protocols are in the 65 and older age range, and are they actually experiencing reversal of functional limitations?
That's very good question. And of course, like our so the majority of our volunteers, like the members of our group, are of age 55 to 60. So it's very close to that range you mentioned. Maybe they are a bit young, but that's also a good thing because they can withstand like more negative influence, or if the like the intervention will go wrong. So maybe to old persons is not also a good idea to try things on. uh, yeah, that's correct. That the effect will be more apparent on older persons, and we should aim for that. And let's see. So the more experimentation, the more like interest in this topic, uh, like the more it grows, the more people it attracts, and maybe we'll find someone who is a bit older and wants also to participate in this study. Let's see.
So my question though orients itself around uh, the demonstration of regression of troubles and therefore functional improvement. Have you seen
Yes.
that? Not biometric improvement, but actual functional improvement, like strength, gait speed, cognition rates, and so on.
Yeah, that's true. The functional improvements, for instance, will be apparent. For instance, in our experiment with this enzyme called 15-PGDR, which should rejuvenate muscles, right? And we expect to see the increased uh, like muscle mass. And this is a beautiful experiment in the way that we can demonstrate this, make it apparent, because we can, for instance, inject the drug into one, say, leg quadriceps, and the other leg will be intact or will be injected with saline. And then we can see the difference between two legs, and we will do like bilateral exercises. So both legs will have the same load, and then we can see how things progress with time. And this will be probably the example of what you've mentioned, like actual physical improvement. But of course, it may fail, and this is totally fine because we're doing like science and we're exploring things. But yeah.
All right. Now we have two on the record questions and then a few off the record questions. And we will start with Mika.
So, as a biohacker, what are your feelings on like how do you feel about sharing like all your not only your results, but also your personal biodata, just with the public. And also, kind of on that, do you think other biohackers also share that sentiment, whatever that is, or do you think there's a diversity in privacy amongst biohackers?
Well, I'm not that familiar with the biohacker community, like in general. So I cannot probably say like
Sure,
what's
just
the
perhaps
current
just for your
state of
team.
affairs there. But in our team, I think it depends. Some biomarkers are okay to publish, some probably not. I wouldn't publish my, for instance, genetic data uh, in public, like in the open access. But some like some, I don't know, like vascular age or some blood glucose. I regularly do posts on Facebook, like sharing my current results. So I don't see any problem with that. But some data I would like to keep private, like
Okay.
genetic data.
For the arterial stiffness sensor, can you give more details on how that works, or is there a place online that we can go and read about it, or is it published anywhere?
No, it's not published. So how does it work? It basically two uh, photoplethysmographic sensors in two locations, in two, like finger on the hand and finger on the and the toe on the feet, and then basically that's it. So no big deal. Measures the time that it took for a pulse wave to travel a certain distance, and then you basically calculate pulse wave velocity out of that. The same principle that medical devices work, but it's like portable.
Great, thanks.
Okay, wait. Well, we will close the we will close the recording. Good. What is the most impressive achievement in biohacking that your group discovered, Alexander?
Well, we have observed like reduction in atherosclerotic plaque in some older people, but we don't really know. Like we are like a bit skeptical about it because we wanna. That's why I was not mentioned in the presentation, because we need more data like to confirm, because it's like too optimistic finding, right? So we should re-examine it multiple times before saying to public that this is like a stable, reproducible achievement. So we would like to.
What
It,
data do you have so far that you, if you can reiterate, what data do you have so far for the evidence for removal of atherosclerosis?
Well, ultrasound examinations of patients, like basically carotid artery scans, like before intervention, a couple of subsequent scans. So yeah, but of course, as someone pointed out correctly, we have to ensure that there were no like environmental factors that can influence the results, or maybe instrumental errors or whatever, because uh, this were well, yeah. So we need some more evidence in favor of this.
Just one more thing. Did you guys get a baseline fluctuation? Like, did you test for like fluctuation of artery health in a normal healthy person with no intervention?
Sure, sure. I've mentioned that in the presentation before. So we measure markers in a longitudinal fashion, right, to have a distribution of values throughout the time. So we have like a pretty clear picture how markers vary, right? To what extent they can uh, like diverge from a mean value, and that allows us to judge whether change was expected or unexpected, right? So for instance, I measure my pulse rate velocity every day, basically.
Okay, now we're going to turn the recording off again. Okay. The final question that we always ask is, how can this group help your work and can help further your work?
Well, one certain thing that everyone can do is to spread their awareness about the the overlooked uh, hallmark or maybe even cause of aging. This is like damage to matrix to the SEM, so that can definitely speed up the progress in that direction. And I don't know, if someone is willing to support us financially or by other means, so you are very welcome. We need your help. If you think you can help us at something, please do not hesitate to reach us at we@emiligroup.net. So this is our email. So please, probably Alison could paste this email somewhere in the description. Yeah.
We will do so. All right. Now I thank you again very officially from everyone at Foresight. It's an honor to have you as a Foresight Fellow next year. Thank you so much for joining. And this won't be the last time that we speak. I hope you have a lovely rest of the day. And I see most of you on September 14 when we discuss chronics. All right, everyone. Have a great rest of your day. Bye-bye.
Thank you. Bye-bye.